So you guys, now that we know about radian angle measure, we can talk about the trig functions of real numbers. And you might be thinking to yourself, well, I thought we already were looking at trig functions. Yes, but what was the input of the trig functions? It wasn't what we consider like a distance measurement or a time measurement. It was an angle measure, right? So what we're talking about here is taking trig functions of numbers, of regular real numbers that can represent a distance or a time. And the radian angle measure combined with the unit circle can help us make that connection between trig functions of an angle and trig functions of a real number. So there you go. The main goal for today is to evaluate a trig function of any real number. What are the applications? Well, you know how the sine and cosine are periodic? In other words, if you think about in terms of an angle, if you go around 370 degrees, right, you'll be in the same spot as if you only went around 10 degrees. Now, don't get the wrong idea. 370 degrees and 10 degrees are not the same angle. They're just in the same spot, right? So if you think about it then, the period of the sine, though, and the cosine, if you take the sine of 370, that's the same as the sine of 10 degrees, excuse me. If you take the cosine of 370, that's the same as the cosine of 10 degrees. So when that happens, we call those kind of functions periodic, when the same outputs start occurring over and over again for certain inputs. We call those kinds of functions periodic. And there's lots of phenomena in nature that are periodic that we can use a sine function, a sine wave. You're going to see it if you graph it in the xy plane. It turns out to be a wave. There's lots of applications in science and in nature of those kinds of functions. So spring vibrations, anything that vibrates, really. Anything in wave form like sound or light might be modeled using some sort of trig function. The tides, the depth at a certain location may be on a pier. That's periodic throughout the day, right? The tide comes in, the tide goes out. The outside temperature throughout the day is periodic. It goes up, it goes back down. AC current is periodic. So all kinds of applications. Unfortunately, we're not ready for the applications yet. Well, we don't get to do the cool stuff yet. We just get to see the definitions and develop the idea of trig functions of real numbers. That's the big idea, by the way. We can use trig functions to model repetitive or periodic phenomena. And in order to develop the trig functions of real numbers, we're first going to develop a new kind of function called the wrapping function. It's going to look strange at first because it doesn't map a number to a number. This function maps a number to a point in the xy plane. But after you get used to that, it's not that big of a deal as far as what it really means. So let's define this wrapping function. So first off, recall radian angle measure. If you have a pi, really it's a circle, right? And you sweep out an angle. In other words, you sweep out a piece of pi, and the crust has length s, so that's arc length. The circle has radius r, and the crust subtends that angle theta. Then theta is equal to s over r. That's how we define radian angle measure. So on the unit circle, what's the unit circle? So this picture down here is a picture in red. That part's the unit circle. What's the unit circle? It's a circle of radius 1 unit, and center 0, 0. And so it has equation x squared plus y squared equals 1. And on the unit circle, by this definition, theta, the angle measure, is equal to s, the arc length. Theta is equal to s because s over r, on the unit circle, r becomes, that's supposed to be an equal sign, hold on. On the unit circle, r becomes 1, so s over 1 just becomes s, so theta equals s only on the unit circle. And instead of using theta, we're using t as our angle. So t is taking the place of theta, so that statement above, that theta equals s, well, we're going to change it to t equals s. T equals t, right? In other words, this arc length here this crust of the pie here, is the same as this angle here because we're on the unit circle. That's the only reason it's the same. We'll look at this picture. So T1 is just a specific value of T. And I want to talk for a second about the wrapping function. But before I talk about that, let's review what a function does. If you see this kind of notation, y equals, say, f of x, then in algebra, in trigonometry, we usually think of f of x as being a formula, don't we? We don't have to. F of x, a function, can be defined using a table, a graph, but we often define it using a formula or just symbolism. And we think of a function is really just a set of ordered pairs where no two different ordered pairs have the same input. The input is represented in this symbolism by x. The input to the function is represented by x, and the output is represented by y. And again, this isn't an official definition, but we usually think of y equals f of x. F can stand for function, but I also kind of think of it as standing for formula oftentimes. So when you say y equals f of x, that's notation for usually y equals a formula in terms of x. And x and y can change. There's nothing special about saying x is your input. T can be your input, as it will be in this section. Formula in terms of x. So some functions that you're used to in the past, y equals x squared, right? Or you could say f of x equals x squared, y and f of x, or g of x, or whatever letter you want to use. The function notation is interchangeable with the output letter, y in this case. So y equals x squared is a pretty famous one. A cubed root function, y equals the cubed root of, 2 minus x, cubed root. So those are formulas you're used to from algebra. Of course, the functions in this class, the main functions are the 6 trig functions, right? Well, let's think about what the wrapping function does. The wrapping function, let me show you in a picture. If we think of the crust of this pie here, the wrapping function, now remember this arc length here is T1, as is this angle measure on the unit circle. The wrapping function is going to take the arc length T1, or the angle, whichever way you think about it, and associate it with the end of this arc length. So the end of this arc length, the end point of this arc length is here. So the wrapping function is going to map the real number T1, the length of that crust of the pie, that arc length of the circle right there, that part of the circle. It's going to map this guy to this point, which we'll call xy, which is the end. If you think about starting at this point, xy would stand for the end of that arc length if you measure positively. So the wrapping function, then, we call it w of t. So wrapping function, w of t, stands for the wrapping function. And what w of t maps to is the point xy, where xy is the end of the arc length. So it's a different kind of function than you're used to, but it still has an input and output. The input would be t. So in this case, it might be better to call, if you want to refer to a specific x and y value corresponding to t1, it might be better to call it x1, y1. So in this case, you could say w of t1 corresponds to the point x1, the output x1, y1. In general, t is your input, and that point that it corresponds to at the end of the arc length corresponding with t is your output. So it's still a function. It still has inputs and outputs. But now the output is an ordered pair itself. Kind of weird, but consistent with the idea of inputs and outputs, if that's how you think of the function. So just to make sure you understand, here's the unit circle once again in a picture. This is the unit circle, x squared plus y squared equals 1. And that means that this point right here is at 1, 0. And let's go ahead and find W0, W for the input 0, pi over 2, pi, 3 pi over 2, and 2 pi. Before we do that, let's label some points in the unit circle. What would this point be up top here? 0, 1. And this point here? Negative 1, 0. And this point down here? 0, negative 1. Okay, so W of 0, if the input is 0, then we're not creating any arc length. We always start at the point 1, 0. And then the input is going to correspond to an arc length that we're going to draw. In this case, a positive arc length, because all the inputs are positive. But if the input is 0, then I'm going nowhere, and I'm stuck at the point 1, 0. Does that make sense? But if the input is pi over 2, okay, I'm going to draw this arc length. Let me make a thicker pen so you can really see it. Okay, I'm going to draw the arc length. Stop me when I get to where I should stop. Stop. How did you guys know? I mean, some people in this class are thinking, wow, how did they know to stop right there at 0, 1, by the way? So that's going to be the output, 0, 1. Yeah, this angle right here is pi over 2. That's pi over 2 is equal to 90 degrees. Remember we talked about that the other day? But the arc length on the unit circle, the arc length and the angle measure, the corresponding angle measure are the same. So this distance that I've drawn in this thick green color has to be pi over 2. And so what do we do to find the output associated with pi over 2? We take the endpoint associated with this arc length. So the end of this arc length, it ends at 0, 1, so the output is 0, 1. Does that make sense? Yeah? Okay. So let's try W of pi. Okay, so let's say I've drawn all this already. Stop me. It's going to be a little thinner this time. Stop me when I get to where I need to go. Stop. It's that output right there, right? What's that output? Negative 1, 0. So W of pi, the input pi produces the output negative 1, 0. Everybody with me? Okay, let's keep going. So I kind of like the thicker pen. Okay, so let's say I start at 1, 0. I go around. Okay, I keep going. Stop me. Right there, right? And so this point's the output point. What point is that? 0, negative 1. And then W of 2 pi, if I start at 1, 0, go around, keep going, stop me when I get to 1, 0, the output of 1, 0. Because 2 pi as an angle on the unit circle is associated with one turn all the way around, one full revolution. Everybody with me on where those points, those outputs come from the wrapping function? So we're mapping a real number to a point. So we want to find W of t for t equals 4 pi over 3. So we're saying, in the language of the last example, we're saying find W of 4 pi over 3. The input is 4 pi thirds. This is an opportunity to review what 4 pi thirds would be as an angle measure. So which quadrant would an angle of 4 pi thirds be in? It'd be in the third. Here's how you get it, you guys. So this, we think of this as an angle measured in radians, first of all. And that's the beauty of it. We can think of it as an angle and as a real number. That's the beauty of radians. Now, 4 pi thirds then, we have to think about, okay, so pi would be the straight angle, right? It would look like that. Going 3/4 of the way around, that would be 3 pi over 2, right? So 4 pi thirds has to be in between 1 pi and 3 pi over 2, because 3 pi over 2 is really 1.5 times pi, right? 4 thirds pi is about 1.3333 pi, right? So that, it's got to be in the third quadrant. Does everybody see that argument? Understand that argument? Okay. So As an angle measure then, I'm going to model the terminal side of 4 pi thirds. And so I'll use a straight line to do that. I know it's in the third quadrant. And I happen to know also that in degrees, the reference angle would be 60. So as an angle measure, this guy is 4 pi thirds. Would everybody agree with that? How do I know the reference angle is pi thirds or 60 degrees? When you're in the third quadrant, you take the given angle and subtract 180 from it, but we're not in degrees, so we have to subtract pi, right? So the reference angle here, alpha for 4 pi thirds, you would take the bigger angle between pi and 4 pi thirds. In the third quadrant, 4 pi thirds is bigger than pi, and subtract off pi. But 1 pi is really 3 pi thirds, right? So if you do that subtraction, does everybody understand why pi is 3 pi thirds? Because 3 thirds is really just 1. So if I do that subtraction, get the common denominator, and do that subtraction, I get pi thirds. And that's my reference angle, which is this guy. By the way, did I have to do this work? No, if the denominator is 3, unless I'm trying to fool you somehow, the reference angle is going to be pi thirds. Okay. So what? Well, what we can do, let me erase the pi thirds for the time being. I'll put it back later. What we can do then to get W of 4 pi thirds, well, okay, think about what the output has to be. If you draw the corresponding arc length, it would start at 1, 0. The arc would start at 1, 0 on the unit circle. And the end of that arc length is the point we're looking for, right? And the end of that arc length is going to occur when we hit that terminal side of the angle. Because this length in green is the same as the angle measure on the unit circle. So the length in green is also 4 pi thirds. Because the radius is 1. S, the arc length, is equal to the angle measure. So this is the output that we're looking for. This point is the output of W of 4 pi thirds. That's really all we've learned so far as the wrapping function goes. So if you can find that point, you've got your output. But now we can just go back to right triangle techniques if we just raise a perpendicular from that point and create a triangle. So the idea is from this point, raise a perpendicular until you hit the x-axis. Okay, actually, I'll just change the whole thing. Does everybody see the triangle here? I'll outline it in red. That should show up good. So this is a right triangle I created from this output point on the unit circle, I raised this perpendicular and created this right triangle. Now remember, the point that we're looking for has coordinates x, y, right? On the triangle, the directed length of the adjacent side to 4 pi thirds is the x value from that point. And the opposite side is the y value of that point. So by the way, what's the radius or the hypotenuse, I mean? 1. So just go back to right triangle trig then. Oh, okay. Well, right triangle trig tells me, well, what function involves the adjacent side x and say the hypotenuse? Think the CAH, ka par SOHCAHTOA, right? Cosine is equal to adjacent over hypotenuse. So we could say then that the cosine of the angle, which is 4 pi thirds, or the length, doesn't matter. You can think of it as a real number. The cosine of 4 pi thirds, either way you think of it, whether it's an angle or a real number, is going to be equal to the adjacent side, which is x, over r, over the hypotenuse, which is 1. And you don't really need to write that down, right? X over 1 is just x. So long story short, if I if I change the order here, I've got the x-coordinate of my point. X is equal to the cosine of 4 pi thirds. And then in a very similar way, what's the sine of 4 pi thirds? It's y over 1, or just y, right? That's, so focus on the triangle here. The angle is 4 pi thirds. You can hardly see it now. Y is the opposite side to that angle. You can think, if you don't see that, you can think in terms of the reference angle if you want. Y is opposite of that reference angle as well. And of course, the hypotenuse is still 1, so y over 1 is equal to the sine of 4 pi thirds. So don't worry, I'm going to get to the punchline here in a minute. So y is equal to the sine of 4 pi thirds. Well, isn't it these values we're looking for? Aren't these x and y? Those are the taken together as an ordered pair. Those represent the output of my wrapping function. Okay, so this is a good opportunity then to review how we find the exact value, because 4 pi thirds has a reference angle that's a special angle. So since we're in the third quadrant, what should the sine be, S-I-G-N, on both x and y? Negative. If you think of all students take calculus, both cosine and sine are negative in the third quadrant. Or just look at the graph. Cosine and or x and y have to both be negative in the third quadrant. So let's see. So the cosine of 4 pi thirds should equal the opposite of the cosine of the reference angle, which is pi thirds. That's how reference angles work, right? So, okay, if you remember, pi thirds is really 60 degrees. What's the cosine of 60 degrees? 1/2. So, but we have a negative in front, so negative 1/2. And then over here, that means y sine of 4 pi thirds means that y is equal to the opposite of the sine of the reference angle, which is pi thirds. And then what would that be? Yeah, the sine of pi thirds is root 3 over 2, and then you got to put a negative in front of it since we're in the third quadrant. So negative root 3 over 2. Sine is 60 degrees, same as sine of pi over 3. So the output then, let's put it all together. The output of 4 pi thirds, so W of 4 pi thirds, has an output of negative 1/2 negative root 3 over 2. This is the corresponding point on the unit circle. So this was not an exciting problem. I'm the first to admit that. But within this problem is the secret as to how to define the trig functions of a real number. This is the big definition we've all been waiting for. You've been on the edge of your seats for all day. The definition is this: the trigonometric functions of a real number t, not an angle anymore, a real number t, involve the wrapping function. So the wrapping function w of t equals xy, where xy is on the unit circle. So it's the wrapping function. Then we can use regular old SOHCAHTOA to define these things. Sine of, we're using t as our input, so sine of t is equal to, well, just to really drive it home, I'm drawing t. T is the real number, but it's also this angle. Let me draw it here, and then I'm going to drop this perpendicular so that, okay, this horizontal is x, this vertical is y, this point then at the end of this arc length of length t is xy. So same picture as before. On this triangle that I've formed, I'm just going to think, oh wait, hypotenuse is 1. Just think about SOHCAHTOA, okay? With regard to this particular triangle, and there you go. You're going to have all 6 trig functions. What's the sine of t going to be, the SO part of SOHCAHTOA? Opposite over hypotenuse, so what would that be? Y. It's the second coordinate of that point, right? Y over 1. What's cosine of t? It's x over 1, right? The co part of SOHCAHTOA, but the hypotenuse, cosine equals adjacent over hypotenuse, but the hypotenuse is 1. So it's the first coordinate of that point, isn't it? What about tangent? Tangent of t. It's the same as before. The TOA part of SOHCAHTOA, tangent equals opposite over adjacent. If you look at this triangle, it's y over x. And then the other three trig functions, you use the same reciprocal relationships we've used in the past. So cotangent, what's that going to equal? It's the reciprocal of the tangent, so it's got to be x over y. The secant of t, whoops. The secant of t, okay, you're going to flip this guy. Oh, it's x over 1, so 1 over x. It's the reciprocal of the cosine. Secant's reciprocal of cosine. And then cosecant, 1 over y. You're flipping this guy. Now, students have trouble with this because they haven't made the connection that this is not really new. The difference is it's for a particular kind of triangle with hypotenuse of length 1, essentially, right? And the input doesn't have to be an angle. I mean, obviously from this picture, you can see that it can be an angle, but you can also think of it, that's supposed to be a t, you can also think of it as this arc length here, this arc length. And that frees us up because if we can think of trig functions of as functions of numbers, then we have more applications than just angles. So it's going to free us up to model repetitive phenomena that's maybe based on time or distance for an input and not an angle for an input.